But what we're going to be doing is the binomial expansion, and we're going to be doing, you know, the funky new method of it, which is I've refined it slightly as well to make it a bit more exam friendly, because in its current form, it could be, you know, it was potentially it could not be marked. So I've refined it slightly as well for you guys, because because this method is new. I've never seen it before because I rented it, or I discovered it, I should say. The examiner will never have seen it before. So when they see it, they'll be like, what the hell is this? And if we start making it even worse for them to read, we'll have a problem. We'll just go over what the method is, how I've changed it for expansions, and then we'll look at a couple of example questions. One quite straightforward, and then the other one a little less straightforward, but not too bad.
Yeah.
I'll set you the hard one to do for homework, and then that's us. Yeah, as usual, just jump in with any questions. If you don't understand, tell me. Yeah, because I want you to understand. But as you know, this is a cool method. So let's share my screen and have a look at the whiteboard. Let me just find it. Okay, so there we are. So we're going to look at, first of all, we're going to look at how to keep a number, and then we're going to look at how to make that more generic. So if we want to do 21, it's the wrong color, don't mind that. If we're going to do 21 cubed, we're going to do is diagonal staircase. So do 1, 3, 3, 1. Below the 2, we do 1, 2, times that by 2, times that by 2, times that by 2. Okay. And then just
multiply across.
Multiply across, thank you. And overwrite, yeah. So you do 1 times 1 is 1. Now here, 2 times 3 is 6, and normally I'd say overwrite it, but it's a lot neater if you rub it out first and then just put the 6. So that's the new thing I want you to do. Don't overwrite. So 3 times 4 is 12. Rub it out. Obviously, it's easier electronically to do this than it is to do. So if you're doing it on paper, use a pencil and then write on it over on pen. I'll rub it out with a pencil, write on it. Use a pen, use something a bit more permanent. And then 1 times 8 is 8. So I need to rub out the 1 and put an 8. Then draw a line below. And in the column, we've got 1, 6, 2 in that column. 1 plus 8 makes 9. 9, 2, 6, 1. Okay, any questions?
No.
Any questions that I had?
No, no questions.
No, okay, happy with that, yeah. So we can do that for any number. Now 21 is quite an easy example because we don't have to do anything with the 1. We'll look at a more complicated example where it's not a 1, so it's not much more complicated. And then we'll also look at what to do. Hello. Just look at what to do if it's like to the power 9. You know, what do we do then? Right. So the requirement that I'd like you to make is don't overwrite, rub it out, because otherwise it looks messy and it's not very clear what's happening.
Yeah.
It's still only half as clear because they don't know, well, where did you get that 1 from? Where did you get that 6 from? Because the 3's gone. Yeah. But it's a bit clearer. When I do the actual binomial, I'll show you a further refinement to make it clear that where the 6 came from. But when you're doing it with numbers, you need to have that number there because it's going to end up in the answer. So you've got to get rid of the 3, otherwise you won't get the answer. That'll become more clear when we come to do it later. Okay, so let's do 23 cubed now. In fact, let's do 32 cubed, because I like 32, the answer. So 32 cubed. Okay, so in the same way, because we're cubing, we're going to have 1, 3, 3, 1. Now diagonal staircase. Below the 3, we're going to do the 1 as usual, times that by 3, times that by 3, times that by 3. But here we have to incorporate the 2 now, because before we just had a 1. But incorporate the 2, we're just going to, of course, do the reverse. Everything has a reverse. So we go up the way, we write a 1 below the 2, and times that by the 2, because that's what number's there. So times by 2, times by 2, times by 2. Next up, multiply across. So it's 1 times 1 times 8 is 8. So I need to rub that 1 out and put an 8 there. 3 times 3 times 4 is 36. So 3, replace the 3 by 6. 3 times 9 is 27, times 2 is 54. So 5, replace the 3 with a 4. And 1 times 27 times 1 is 27. With 2, and then you can just make that one a 7, that's okay. Draw a line, you've got 8, 6, 7, 5 and 7 is 12, so carry the 1, 2 plus 1 is 3.
Cool.
Isn't it? Yes. Yeah, so I'm explaining this, but when you do it manually yourself, it takes a quarter of the time, you know, you just got 1, 3, 3, 1, 1, 3, 9, 27, 1, 2, 4, 8, multiply across, that's the answer.
So can you apply this method to, say, x plus 1, x plus 2?
Yeah, it's the exact same method for x plus 1, x plus 2. So, well, the answer's already there. We don't actually have to do any more work from here on in. If you're doing it for x plus 1, or x plus 2, or whatever. So to show you the comparison, if I wanted to do 2x plus 1 cubed, I actually don't have to do anything from here on in. Okay, if I've already done 21 cubed, the answers are already there. Because the reason I do this diagonal staircase is because the boxes underneath, I call them x boxes. So we can have x's there. So 1, 2, 3, 2, and 1. So I'll just clear that up a bit. Get rid of them. Okay, so that tells you how many x's there is. So you read from the bottom if it leads with x, which is what this system is designed to lead with x. So it will be 8x cubed, because there's 3 boxes there. 1, 2, 3. Plus 12x squared, 2 boxes. Plus 6x plus 1. It's the same numbers. It's really, we're just concerned with the numbers, and the diagonal takes care of all the powers of x. It's designed to tell you what they are. So 8, 3 boxes, 8x cubed. 12, 2 boxes, 12x squared. 6 in a box, 6x, 1, nothing there, so just 1. Any questions?
Oh, no question.
No? Okay. So if you want to do 3x plus 2 cubed, we'll just use the answers from there. So reading upwards, it's going to be 27x cubed plus 54x squared plus 36x plus 8. The x's are all there. The system is set up to tell you what the x's are. All right with that so far?
Yeah, great.
Any questions? So,
No.
okay, cool. So let's say what we can do now is we can actually use this as a template to find anything else. So if we wanted to find, let's do it a different color. Wanted to find 2x minus 1 cubed. I don't need to do that all over again, you know, I don't need to sort of reinvent the wheel. The answers will be the same anyway, but obviously there's a minus in there. And all you do is you just put minuses every second one. So it would be minus 12 minus 1. So you just change that to a minus and then change it to minus. That's it. Yeah, so because doing the minuses is a bit of a pain. So you can avoid that completely by just doing the positive version. And then at the end, just go, okay, just switch the minuses out. So it's always the second term and then 2, 4, etc. It's, you know, it skips a sequence, skips a step, so it oscillates minus, plus, minus.
Ooh.
So same for 3x minus 2. Yeah, 3x minus 2 cubed will then become minus 54x squared minus 8. Okay, so that's the underpinning process of it. Now, if you're doing this in an exam, you don't want to be doing 21 cubed to figure that out and then apply it to 2x plus 1 cubed. You want a fast way. So I'll just show you what I'd expect you to write in the exam. So if you're doing, let's do that same one again, 3x plus 2 cubed. Do the same thing. It's all exactly the same. The 1, 3 times by 3 times by 3, and then the 2, so 1, 2, 4, 8. Now here, to show the examiner you're working, instead of, because we're not trying to figure out what 32 cubed is, what we can do instead is just write the answer here. So just do it to the right. So 1 times 1 times 8 is 8. 3 times 3 times 4 is 36. 3 times 9 times 2 is 54. And 1 times 27 times 1 is 27. Okay, so they're the numbers. And then you just count the squares again. So 1, 2, 3. So it's x cubed. Sorry, that's not very well written. So it's x cubed, x squared, x. Yeah, because x squared and x, and nothing on top. So then you can say, well, I'm doing it in a column instead of a row, which is fine. And then if you, I would write it out then in a row. Whoops, wrong way around. So reading from the bottom, 27 x cubed. 27 x cubed plus 54 x squared plus 36x plus 8. That's your fast binomial expansion. I've actually had to incorporate more work for the exam by writing the same thing twice, but I don't really have much choice. I've got to show some working there. It'd be a bit too jarring if the examiner is going to be like, well, how's it come up with 27? Where's that come from? Where's 54 come from? If you get rid of the 3, there's going to be a question about that. If you set it up like that, it tells you what the x is going to be. It tells you what power of x you have. And it's quite a little bit more work, but still pretty fast. Just an I mean, I would never do it in real life, but just for the exam, you need to sort of show something. All right.
Great.
Yeah. Okay. Any questions, Rahat?
No questions.
Oh, I'll just close this. Thank you. All right, so let's have a look at how to find the diagonal numbers. Because the thing is that if it was to the power 9 or something, I don't expect you, or nobody expects you to know them. And traditional ways you use your calculator, which is fine. But there's a just as fast way, really, which I think is a bit more fun. Just figure them out yourself. And the shape of it tells you what they are. So we don't need to use the calculator. As soon as you use the calculator, you've lost the connection as well. So let's just do something straightforward, like hopefully straightforward. Let x plus 1 to the power, what should we go with? 7? Okay, so basically I need to know the coefficients for that. So just do diagonal 1, and then always do whatever the power is. So you start with 1, then 7. Okay. And from there, all you do is just take away 1. And you can go all the way down to 0. We're not going to need that, but you can do. Halfway is actually enough. But if you want, for now, I'll just do the whole thing down to 0. Okay, so what I want to know is, what's the next number in the staircase, right? Well, the thing is that actually it's in front of us, because all you have to do is times the number that we have, which is 7, by the next number in the list, which is 6. So that's 42. And then you divide by its position. So 7 is the second number down. So you do 7 times 6, which is 42. And then divide by its position, which is 2. So that's 21. So you put 21 there. Next up, you do 21 times by 5, the next number along, divided by its position, which is 3. So you can do them. Normally, if you're doing these, it's good to think what's the best. You can do them any order, times or divide or times. So here, divided by 3 first would make more sense. So 21 is the third number down, and 21 divided by 3 is 7, and times that by 5, which is next. So 5 7s 35.
Okay.
Next up, we're going to times that 35 by the next number along, which is 4. But we're also going to divide by 4, because that's the position. So times by 4, divide by 4, gives the fourth number down. That just gives the same thing again. So you get 35 again. And when you get repetition, the nature of this is that it then just does the reverse, because everything has a reverse. So the next number, we could figure it out in the same way, but we don't need to. We could do times by 3, divide by 5, but that will just give 21. Which is just the opposite from before. The next number is going to be 7, which would be times by 2, divided by 6. So 21 times 2 is 42, divided by 6, 7. But we don't need to do that. We can just know, we can see the pattern. 1, 11, 21, 35, 35, 21, 7, 1. And there are coefficients. Yeah, with a bit of practice, you get used to doing that. Multiply by the next, divide by that, or divide by it. Depends what the number is. It'll always be nice. It'll always fit nicely. That's the thing. We don't have to do any complicated calculations. And we can do it for any power. So we can do it for power 11, power 20, whatever, power 50. Now the multiplications get a bit big, but for 10 or below, you can do it manually. It's fine. The numbers are okay.
Yeah.
Question.
Yeah, please.
How do you get 21? Because 6 times 5 divided by 3 is 10.
The position is of this 35 here. Yeah.
No,
Is-
I'm as in the 21. I understand how you got the 35 because 5
Which
times
21?
4 divided by 4 is 35. But how do you get the 21?
This 21?
7, 21. No, the first one.
The first one. Okay, yeah. So this one, that's the first one we found, isn't it? Yeah. So you do 7 times by 6, which is
Is 7 times by 6, which is 42.
Yeah, and then divide by the position of 7, which is 2. It's in the second number down.
Yeah, 21.
That's it, yeah. So you divide by position times by the next number along,
Okay, yeah, that's fine.
or times by the next number along, divide by position, whatever's convenient. Or ignore the number completely and just do that division. So if they're nice numbers, like 6 divided by 2 is 3, because you got 6 there divided by 2, which is the position, is 3, times that by 7, 21. So you've got a number of options, but they'll always be nice. You always get a nice number out because the Pascal's triangle is nice. It's not going to be some horrible number. Okay, so then to expand to get the actual value, then the values of x will be just the x boxes here. So it's 1, 2, 3, 4, etc. So x to the power 1, x to the power 2, x to the power 3, x to the power 4, 5, 6, 7. So it'll be x to the power 7 plus 7x to the power 6 plus 21x to the power 5 plus 35x to the 4 plus 35x cubed plus 21x squared plus 7x plus 1. Okay, so now we can do any. Yeah, and the thing is that we can literally do any because it doesn't have to be a positive number. It'll still work with negative numbers or fractions. This method, yeah. So this the advantage really is that this technique is the only technique you need for all binomials of any kind. Whereas the current method is that there are 2 different ways, 2 different approaches. This is the only one you need to know. Generate the diagonal. That's it. In this case, for x plus 1. But if it's different to that, 2x plus 1, you just bring the 2 down. So I'll show you that now. Let's do a different path because of the just to exercise our ability to find any line of Pascal's triangle. So now we can find any line of Pascal's triangle, and we can even find lines we can't see, which will come later on, a bit later on in this lesson. So let's say we want to do 2x plus 1 to the power 6. Right, I think most people, most math students, when they see this, they sort of go, oh, that's going to be a pain to figure out because you've got to do all terms and you've got to write them all out. It takes ages. So here's the faster way. So you just do 1, 6. Now we need to know the next number. So first thing is we do 5, 4, 3, 2, 1. We don't, as you saw, we didn't actually need those, all of them, just the first half. And then we just do 6 times by 5, which is 30, divided by position. So the second one down. So 30 divided by 2 is 15. Then we do 15 divided by 4, times by 4, sorry, which is 60 divided by position, which is 20. 20.
So is it 15 divided times by 4 and then divided by 3, or is it 5 times
number? 4? It's the number that we get. Yeah, you use the number that you get to times by the next thing.
So 15 times by 4, 4 is the third position along, so you get, yeah, okay, so divide by 3 then.
Exactly.
Okay.
Then you do 20 times by 3, which is the next number along, divide by position, which is 4. So that's 60, divided by 4, 15. So we've got repetition. And as soon as you get repetition, you can use the pattern to finish it off. So that line of Pascal's will be 1, 6, 15, 20, 15, 6, 1. So what to do about the 2x? Well, like before, we're just going to we're going to put a 1 there, times by 2, 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 times by 2. The 1, don't need to do anything, because it's just going to be 1 times 1 times 1 times 1 times 1 times 1. There's no point. Can do if you want to, but why bother? So because we're doing this exam style, we need to write out the answers. So the top line will be, sorry, the bottom, yeah, top line will be 1 times 1, which is 1. And then 6 times 2, which is 12. 15 times 4, 60. 20 times 8, 160. 15 times 16, 240. You might not know that off the top of your head. What happens is you start to get to see a lot of the same multiplications when you do quite a few of these, and often they are these same numbers.
Yeah.
So 15 squared is 225, plus 15, 240. 6 times 32, 192. Again, it's another number that appears quite frequently. 64.
Ooh.
Then we do our dots. So it's x squared, x cubed, x to the 4, x to the 5, x to the 6. So x to the 6, x to the 5, x to the 4, 3, 2, 1, 0. So this is, more work than we'd normally do, but just for the exam. So 64x to the 6 plus 192 x to the 5 plus 240 x to the 4 plus 160 x cubed plus 60 x squared plus 12x plus 1. Ooh. So I'm just writing it out in a row for exam purposes, really, because it might be a bit jarring to the examiner if they see it in a column. That's not something they're used to. They've probably never seen it before in a column. I'd bet money on that. So write it in a row and they'll go, oh, okay, he's got the right answer. How's he got that? And then you can see, you'll be able to see 1 times 6. 1 times 64 is 64. Oh, okay, something's going on there. Then hopefully have a discussion about it at the examiner's meeting. Is this acceptable or not for future exam?
Right.
Don't see why not. You've got all the numbers there, which was what anybody else would write. You just write them in a column instead of a row. That's all.
Yeah.
So yeah, it's just a lot easier. Oh, it should be a lot easier, a lot faster, a lot more fluid.
Yeah.
And also there's lots of benefits. So if you want to find, if it was 2x minus 1, that is actually a bit nasty with negatives and easy to make a mistake. Whereas for us, we just need to we just change the second term every time. So if it was 2x minus 1 to the 6, say, still find 2x plus 1 to the 6, but change every second term. So it'll be minus 192, minus 160, minus 12. Okay, guys?
Yeah.
Any questions?
No.
No.
Brilliant.
Would you, sorry, one question.
That's a legendary Rahat move. No questions. Oh, I've got a question. Go on, yeah.
Say, would you ever get like a, say, like a binomial expansion where it's divided by something?
Yes.
2 over 3x plus 1 over 3, something like that.
Of course. And you just do the same thing. Exactly the same. So I think actually one of the examples has that. If not, I'll do one. So if it's like, let's say it's a third x plus 1. Then you just do 1 times a third, times a third, times a third, times a third. Whatever the number is, you just go in the same way. So it's 1/3, 1/9, 1/27. It's just the reverse. So instead of being 3, 9, 27, it's 1 over 3, 1 over 9, 1 over 27.
So in this case, if it was, say, a half x plus 2,
yeah,
instead of having 1, 2, 4, 8, 16, 32, 64, you have a half over 1 over 2. Sorry, what would that first one be?
Well, just like you said. So if it okay, let's write it. So if it was a half x plus 1 to the 6, say, but just below that, you'd write 1. Always write 1 first, times by a half. Times by a half. So the numbers are all the same, look, it's just the reciprocals of them. Instead of 2, 4, 6, 2, 4, 8, 10, what the heck? 2, 4, 8, 16, 32. 1 over.
So if it was 3 over 2. then you have 1 1 times 3 over 2, whatever that is, times 3 over 2, so on, so on.
Yeah, well, it's just again, it's just that there's no difference. Okay, it's always the same method because if it was different, it wouldn't be very good. So times by 3 over 2, times that by 3 over 2, and if you times that by 3 over 2, you just get square numbers, 9 over 4. Times that by 27 over 16, so that sorry, 27 over 8. So you get cube numbers, and then you get fourth numbers. It's just the same. It's all the same. Yeah, there's no difference. Whatever that number is, just keep multiplying it. So you start off with 1, times by 3 halves, times by 3 halves, times by 3 halves, times by 3 halves, etc. What doesn't matter what it is. That's the whole point of this rule, the system. Yeah. Shouldn't have any nasty surprises. So let's have a look at a kind of sort of straightforwardish question. Let me just find it. What is the coefficient for x cubed in 2x plus 4 to the power 8?
So you want to do the first 3 terms, really. You don't want to do the whole thing.
Yeah, well, the traditional way is that you just go straight to the term, but our method is so fast that we can just do our normal technique and then we get there just as quickly. So let me script. So that says what's the x of x to the 3 term? What's the x cubed term coefficient? Sorry, into x plus 4 to the 8. Have you got any questions about that question before I show you how to do it?
No.
No? Okay. So I'll show you how to do it. Yeah, I'll just tell you. So we want the x cubed term, right? So we just go 1. We need 8. So it's 8. Take away 1, take away 1. Don't have to go very far because I just want the x cubed term. So I don't need to go crazy all the way down to the end. Do 8 times 7, which is 56, divided by 2. That's the x squared term because it's x squared. So I need the next one. So I do 28 times by 6 divided by 3. That's a bit fiddly. So it makes more sense to do 6 divided by 3, which is 2 times by 28. So just change the order. Yeah, because we have to do 28 times by 6 divided by 3. Just change that to 28 times 2 in our mind.
Yeah.
So that's going to be our x cubed term, 56. So I don't need to do any more work on that front. Next up, below the 2, 1, 2, 4, 8. Okay, so that's our number there. And normally what we do is we work all the way down and come back up again, but we can be a bit cleverer than that and just instead just do 4 to the 8, 4 to the 7, 4 to the 6, 4 to the 5. Because that's what equivalently we are doing, you know, when we start from the bottom, we do 4, 3, 2, 1, we do 1, 4 times by 4 times by 4 times by 4. So we're doing that anyway. So we're not really concerned at the moment what those individual numbers are. So we can just take that shortcut. So the coefficient will be those 3 numbers. Whoops. The coefficient will be those 3 numbers times together. And you're not expected to do that manually. So just use a calculator for that.
458,752. I got
458, 752. So 4 to the 5, 752. So that's a big number, 4 to 5 times by 8 times by 56. Yeah. Cool. Nice big number like that. Yeah. So we 4, 5, 8, 7, 5, 2 x cubed. So the coefficient is 4, 5, 8. 1, 2, 3 x cubed. 4, 5, 8, 7, 5, 2. That's fine. The numbers are all there. 56, 8, 4 to the 5. You know, the examiner can see that. And that's just as fast as trying to figure out what's the correct powers you should use and stuff like that, and sort of narrowing in on it. I think that's quite good about it. It's kind of like a handrail to make sure you get the right value, because it's right there, x cubed. You can see it. It's 3 boxes. That must be the x cubed term. You can't be wrong with that.
Mm.
Yeah, I mean, you could do it faster than that. Some people might argue, oh yeah, you could do it faster, but it doesn't matter, because when you get fast at it anyway. You know, this is fast. It's taken this long to explain it because I'm teaching, to do it because I'm explaining it. But if you did it manually, you would fly through that. But also, what's going to happen is that you get to know the coefficients. You know, you're not going to have to refigure them out every time. And in the Pascal triangle, you start to get to know them. They're not so much of a mystery. You know, why are they that? And we'll see also that later the benefit will be what to do with more advanced binomials. So, is that okay, Rahat?
Yep, all good.
Yep. Yeah, brilliant. So let's have a look at another example like that, a bit of a longer question. I think I'll put this in the chat to you guys. So we've got a binomial expansion, 2 minus 5x to the 8 to find the number of terms. The fourth term, when the expansion is in ascending powers of x, and the greatest positive coefficient. So I think those are like, I mean, a normal student would go, what pain all that is, right? But we're going to do it in, you know, under 30 seconds, hopefully. Anyway. The first thing is the system works with positives, so we're going to change that to a positive. So 2 plus 5x, we'll change the negative, we'll put the negative in later. And also it works with leading x. It doesn't matter that it's leading with 2, but the system works better if I just switch it around and do 5x plus 2. So we're going to do 5x plus 2 to the power 8. And figure it out. Now, part A, what's the number of terms? It's always one more than the power, because with binomial, there's always one more. So that's just
Do you say one below the power?
One more, yeah.
Yeah,
We'll see when we do it, there's one more. But there's always one more, because if it's we saw it cubed, it's 1, 3, 3, 1. That's 4.
Yeah.
The squared, it's 1, 2, 1. It's 3. Yeah. If you look at the previous example we did, in a minute, we'll see it's always one more. So number of terms is going to be 9. The fourth term, when the expansion is in ascending powers of x. So fourth term, let's make a note of that. Ascending x.
Should we be seeing Scribbler or the question?
Yeah, I'm just going to switch over. I'm just making a note. Greatest positive coefficient. Okay. Well, to find the greatest positive coefficient, we haven't got much choice but to do the whole thing anyway. So let's get on with it. So here's the question. So I've changed it to 5x plus 2. Remember, it's going to be 2 minus 5x to the 8. That's what the final thing needs to be, which is why it's asking about the greatest positive coefficient. Okay, so we do the 8. We're going to do our 8's lowercase. So we do 1, 8, 7, 6, 5, 4, 3, 2, etc. Can you see that okay? The trouble is I do this method so fast now that I write it too quickly. So we're going to do 8 times 7, 56, divided by 2, 28. So we've seen that number before. 28 times 6 divided by 3 is the same as 28 times 2. 56 divided by 4 is 14, and times by 5, the next number along, is 70. Is that okay so far, guys? So I go a bit fast on that because it's an easy thing to do.
No, that's great.
Yeah. And okay, so 70 then times by 4 divided by 5. Well, we just had that. Yeah, times by 5 divided by 4. So times by 4 divided by 5. Let's divide by 5 first. That's 14. Times by 4. That's 56. And we've got repetition. So we're going to go 28, 8, 1. 28, 8, 1. How many terms have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, of course. Let's be back at one sec. Just need to close the window. Okay, any questions so far?
No.
So that's Pascal's triangle fast, going along that row. Next up, we want to know what the fourth term is. Yeah, because we got the we know the first question is how many terms? 9. What's the fourth term in ascending powers of x? All right, so let's figure out what it's going to be. So we've got 5 and we've got 2. So we're just going to below the 5. We're just going to write 1, 5. Times that by 5. Times that by 5. Times that by 5. And because the number's starting to get a bit big here, you don't need to crack out your calculator.
3125. Then 15625. Well, 78125.
Way ahead of me. Yeah. And then
390625.
390625. Cool. And then we're going to go the other way up with the 2. So 1, 2, 4, etc. etc. 1, 2, 8, 2, 5, 6. Okay, so we've got everything we need to know there. And we want to know the fourth term in ascending powers of x. So that means that we need to read down that way. Because it's x, x squared, x cubed. And there we go. That's the fourth term. The x cubed term is the fourth term because 1 times 1.
Yeah.
That's 1. So we'll just multiply those numbers out. So 56 times 125 times 32 x cubed, whatever that is.
224000.
2, 2, 4. Say again, 0, 0, 0.
Yeah.
Nice round number. All right. Now, the question is that positive or is that negative? Because remember, we've got to put the minuses in. Right.
It's a negative, right?
It's going to
Yeah.
be positive
You say positive. What do you say?
on the
Orhan?
negative.
Well, I said
You-
negative. It starts with a positive, then negative, then positive, then negative again. So if you're going to the fourth, which is x to the power 3, you should get negative, right?
Yeah.
So 2 to the 8 is going to be positive. So the next number will be negative. So that'll be negative. Yeah. Negative, negative. So there's going to be a negative there.
What if they were both negative, say -2, -5x? Would that you just do that as normal? Ignore all the negatives?
Yeah, all you could do is just take the minus sign out of it, factorize it out, do the whole thing, and then times everything by a negative at the end.
Everything.
Yeah.
So everything will be a minus number.
Yeah, because it's all negative, isn't it?
So in that case, it will be 1 times 1 times 256, and that answer would be minus 8 times 5 times 128. That would be minus, everything would be minus then, right?
So let me come back to that because I don't want to pollute what we're explaining here. Yeah. It depends actually on the power. So if everything's negative and it's a positive power, it's an even power, then that would then get rid of all the negatives. If it's an odd power, it would all be negative. So it sort of oscillates between the two in a more general ground way. So it depends on the power. But camera's done something strange. Let me just fix my camera. Stop. There we go. Let me come back to that. Okay, that's a good question. Yeah, what about this situation? Always the best kind of question. Maybe have a go of it yourself. Do a basic one, entirely negative. See what the results are. See what you can learn from it.
Mhm.
So that's the fourth term in ascending powers of x anyway. 220 minus 224,000 x cubed. Okay, now it's asked. This is what's quite nice about this question: is it asks for the greatest positive coefficient. Now we know there's no point looking at the negative. We know what to examine the positives, right? So we can use a bit of logic and go, well, okay, well that's positive. That's positive. That's positive. And just so figure out all the positives and see what they are. Yeah. That one's positive as well. So we're going to have to effectively, half the expansion to figure out these ones. So you need to do 28 times 25 times 64, whatever that is.
Uh,
When it says the
That's-
largest coefficient, does it mean the number next to the largest power of x, or just the largest number next to any value of x?
Yeah, the latter, because otherwise it'd just say what's x to the power 8 going to be.
Okay.
What was that answer, Ollie?
for 28, it's 1,750,000.
Nice. Okay, that could be a contender. Then
And then
70 times 625 times 16.
700,000.
Okay, so I won't even bother writing that.
Mm.
28 times 15,625 times 4.
Oh no, sorry, I was doing it the other way around. Sorry, that 1 million one was for 28 times 15.
Oh, that's 28. Okay, yes, that is 1750. All right.
Yeah.
That makes probably more sense. 28 times, yeah, because that does seem a bit high for 28 times 25 times 64 in retrospect.
Sorry, and then the one you just said then was 44800.
70 times 65 times 16.
28 times 25 times 64. Sorry.
What was that again?
44,800.
Okay, so too small to worry about. 70 times 65 times 16.
That's 700.
Say again.
700,000.
Okay, so that's 2 there as well. And then this one will be the coefficient times by x to the power 8. That's 2 there as well. So that's the answer. 1,750,000, 1.75 million.
So what was the question? Find the largest coefficient to a positive value?
Yeah, you just asked me that question.
Okay.
Trying to find the greatest positive coefficient, yeah. So we just looked at all the positives. Numbers, because there's going to be negatives. There's intermittent oscillating ones. Yeah. They're going to be negatives. No point looking at those. So just times across, see what they are. I've just written down the largest one, not all of the answers. But in the exam, we'd have to do all of them. Okay, man?
Yeah.
That's it. So there are 2 questions I wanted to look at with you. Any questions about any of that?
Oh.
Yeah. So greatest positive coefficient was just trying to, what you could do is just expand the entire thing and find out what it is. So if we see if all that's true by checking, it's always good to check. So let's have a look at what the actual answer is in case it's wrong. It could be. So 2 minus 5x to the power 8. Pascal calculator do it for us. There we go. There it is. And the answer is, oh, my iPad just froze. 1 second. There we go. So I can't move it because it did something strange. Can you see that? No. It's not letting me move it for some reason. It's just frozen up. Anyway, you can probably see there that the number 175000 features. And the rest of the numbers we have are correct. So -224 as well, we found that earlier. And yeah, that would help. That would seem to mean that we got it right, yeah. So it's always, whoa, look at that. Always good to check, isn't it? There you go, I can move it now. I did it again so I can get a clearer look at it. So if we look at the answers, does it agree with it? There's 256 there. So this is, for some reason, it writes it the opposite way. The biggest coefficient, yeah, 1.75 million. And our XQ term, the fourth term, 1, 2, 3, 4, -224,000, as we said. Okay, cool. So let's move on to our final thing. So you also be asked, oh, let's answer your, oh, we did answer your question, didn't we, Raha, about fractions. Okay. So you also be asked to expand brackets where the power isn't a whole number. Because, you know, we have to look at all the possibilities in maths. So we could have something, just as a straightforward example, 1 plus x to the power -2. So that's the -2. Okay. Or x plus 1 to the -2, whatever. Now to do this, normally you require a different formula. You pull out a different formula from the bag of golf bag of clubs of, okay, I need another formula for this. We're just going to use the same, exactly the same technique to do this. All right. So we'll write 1 and -2. Do this diagonal guy. So do 1 -2. And then we need to do the same thing. Keep taking away 1. So let me just try and stay a bit more inside that box to differentiate it. So -2, -3, -4, -5, -6. Now the thing is, we could do that forever. Yeah, we could go on infinitely long doing this. And this turns out to be an infinite expansion with infinite number of terms. So we don't want to do that. It'll take us a while. So in the exam, I'll probably say something like find the first 3 or 4 terms of this expansion. All right. We're kind of halfway there already because we're going to find the next term here. So this next term is going to be -2 divided by 2, which is -1, times by the next number, which is -3. So that's 3. Then we take 3 divided by 3, which is 1, times by the next number, which is -4. -4 divided by 4, because that's its position, times by the next number. So that's 5. Divided by 5, times by -6, and so on. Okay, so we could go on like that forever, but we won't do. And because of the way we set it up, we've got our x squareds here. So sorry, x is here. So that's x squared x cubed, x to the power 4, and so on. So let's go straight into writing it as 1 plus x to the minus 2 is, and we normally will do it down the staircase because we're leading with the 1 there. So 1 minus 2x plus 3x squared minus 4x cubed plus 5x to the 4 minus 6x to the 5. So the number of dots here below the 1 and to the number is telling us what power of x, just like we had before. Plus dot dot dot, which means it keeps going. Any questions, guys?
Is this where we write like orders for power of x? Sorry,
Yeah, that was just on the when we did this. You and me, that was just a computer thing. In the exam, we just put dot dot dot.
all right.
You're not expected to know that yet. I suppose you could do if you wanted, but not expected. Okay, so that's. Any questions on that? Any other questions on that, Rahat?
No questions.
So as you can see, exactly the same technique, nothing to change. Same, we find the coefficients, we know the x powers, done. Okay. Someone might say, okay, well that's fine for a simple one like 1 plus x minus 2, but what if it's not that? What if it's 2 plus x minus 2? Then what do you do? Now, to do this, the first thing is that the system works with it the other way around. So I need to flip it around. So x plus 2 to the minus 2. That's just to do with our use of x as the number that will come down. Well, that'll make more sense when we do it. Now, because this is an infinitely long series, I've got to get rid of that 2, because if I can get rid of the 2, I'd make it a 1, then I've just got to put 1, 1, 1, 1, 1 to any power, and that doesn't have any effect. So I want to get rid of this 2, and the rest of it will take care of itself. Okay. Because if I tried to do this normally, I'd have to have the 2 to the power infinity at the top. It wouldn't really, basically the whole thing breaks. So I need to take the 2 out. So what I'll do is I'll just factorize the 2 out of it. So how am I going to do that? Well, I need to times the whole thing by 2 over 2. Which looks like that. Because 2 divided by 2 is 1. It's not doing nothing. Next up, I will divide throughout by 2. So I'll just put that 2 into the bracket if you like. I'll leave the 2 out here. So it becomes x over 2 plus 1, which is what we're trying to get. That's to the power minus 2. We just need to get a 1 there. Our lives are, we can't even do it if it's not a 1 there. So our lives are going to be a lot easier as a result of that. And we could do this for any, we could do this for any expansion. We could have done it earlier with the positive whole numbers, but the numbers aren't as nice then. So there's no point. Next up is we're going to separate this off into 2 parts. So we do t to the minus 2 times by x divided by 2 plus 1 to the minus 2. Okay. Is that okay so far, guys? I'm just doing some factorizing it. And then using the rules of indices to say, well, brackets means multiply. So 2 to the minus 2 times x over 2 plus 1 to minus 2. That minus 2 should be a bit tighter to the bracket. There we go. Okay, next up, 2 to the minus 2. What's that? What does that equal?
Quarter.
Quarter. Thank you. Yeah. So the final thing is 1/4 x over 2 plus 1. to the minus 2. So now we just do the normal expansion on that x over 2 plus 1, just like you said about fractions as well. That's going to come up right out now. But we're going to times, and then we're going to finish the whole thing divided by 4. Or times by a quarter, whichever way you want to look at it. So I'll just write it down here. So we're going to have 1 minus 2. Now I've already actually figured these out the top left, so I know it oscillates. I won't, just for the sake of time, I won't do it again. So there's the coefficients for minus 2, 1, minus 2, 3, minus 4, 5. We saw it earlier up. If you want to rewind 2 minutes, you'll see it. Then we just do below that, like you were asking about, it's a half. So we write a 1 times by a half, times by a half, times by a half, times by a half. And the ones aren't going to do anything. So we don't have to worry about that. We've got our x's here. So the first 5 terms will be, reading down from the top, so 1/4 in front, times by this entire expansion, which is 1 times 1, minus 2 times a half x, so that's minus x, plus 3/4 x squared, minus 4 over 8, that's minus a half x cubed, plus 5/16 x to the power 4, etc. All right, that's it.
Mm.
Then we could times that 4 out by 4, so it would be 1/4 minus x over 4 plus 3/16 x squared. But we don't have to, we can leave it there. That's it, done it. Done the binomial expansion. So if it doesn't have a 1 in it, and it's not a whole number power, and it doesn't have a 1 in it, you have to make it 1. You have to factorize it out, because otherwise you can't use this system. Because we want a 1 here, because we just have 1, 1, 1, 1, 1, and that makes it 1. Because times by 1 doesn't do anything. It's not going to change its value. So the entire benefit is it's all the same system, got a diagonal staircase, but the same way of figuring out the diagonal staircase, got the same drop down of powers. Yeah, I mean, you'd have to do it anyway. You have to get it to 1 anyway if you use the normal formula. So it's not losing anything here. No waste of time or anything. It's not like we're having to make an exception for this method. It's what you'd have to do anyway. Just a lot more straightforward, because we can easily find the diagonal. We can easily find the numbers below. And then we'll reduce times together. It's already all set up, so you know what the x powers will be. And that's it. We even get a bit of practice factorizing into the bargain, as well as some indices practice. Any questions?
No.
Okay, cool. So this would even apply if there was a number in front of the x as well. So that's the other possibility. So if we had, I won't go through it, but just to say it's the same process, so that you know. So if it was, say, 4 plus 3x to the minus 2, yeah, got a number in front of the x as well. We're going to have to take that 4 out, which will generate 3/4, and then you just do the same thing, 3/4. So 1 times by 3/4 times by 3/4 times by 3/4. Then you change the order of it for that. So we'll take the 4 out. So I'll divide. You don't have to have this intermediate step. I'm just doing it for teaching purposes, which is but writing 4 with a 4 next to it. You could just divide by 4 in one go. So you could just do this next line. In one go, and that's acceptable. Then change the order. So that's going to be 1/16. 1/16. Change the order for the expansion system that we've got. And then we just go through the same process. But here it's going to be 1 times by 3/4 times by 3/4. That's meant to say 1 3/4 9/16. Sorry, I've got a bit messy there. 1 3/4. I'm a bit limited because the rows are so narrow that I'm struggling to get 9/16 in. But if on proper squared paper, you got plenty of room, etc.
So essentially, you turn one of them into 1. If it's like 4 plus 3x or 5 plus 10x to the power minus whatever, you have to turn one of them into 1.
Whatever
one
the
that's
number, not 1, you're going to make it 1, yeah, because otherwise you're going to have to find this. When you do this, if this is a number like 4, you need to start down here at infinity, down here at infinity.
Okay.
And work it up, or do the power thing, but the power here will be 4 to the power infinity. That's a bit of an issue. Yeah. So what we'll do is we reduce the problem by taking it out and making it 1. We could do, like I say, we could actually do the same thing with 2x plus 1 cubed. You can take the 2 out, or 3x, well, whatever, 2x plus 5 cubed. You could divide it 3 by 5 and do the same thing, but the multiplication is then a bit fiddly. Not nice. Because you've got to do 6 multiplications, and they're all horrible. If you don't bother doing that, it's fine. But you could do. It's possible to do that. Okay. One final thing you asked me about there, Rahat, is what if they're both negative? So I'll just revert to a simple minus x minus 1 cubed scenario. Yeah. Then what? What you could do is minus 1 x plus 1 cubed. Just take that out. And then just do minus 1 cubed times by x plus 1 cubed. So you end up with x plus 1 cubed as normal, and then the whole thing's going to be multiplied by minus 1 cubed. Well, that's minus 1. So that'd be negative. I don't need to bother doing that because it's x and 1. So it's x squared, x cubed. It'll be minus 1 times x cubed plus 3x squared plus 3x plus 1. Makes it all negative. But
Okay, so just take the one of them out. Take the negative out, and you can just do it as normal. Just times it by minus 1 at the end.
minus 1 cubed, yeah. Minus 1 cubed.
Which is just minus 1.
Minus 1. But if it's a positive power and you pull that trick, what we're going to have is,
So if it was x to the it was to the power 4, then that would be 1 times x to the power 3 plus 3x to the power 2, right? Because
Right,
1 to the power of.
it's the power 4, the numbers are different, aren't they? So it's going to be 1, 4, 3, 2, 1. So 4 times 3 is 12, divided by 2 is 6. 6 times 12, divided by 3 is 4. 1. There's 1. So it's going to be minus 1 to the power 4 minus by x to the 1 plus 4x cubed plus 6x squared plus 4x plus 1. But minus 1 to the 4 is positive.
Mm-hmm.
So it's going to stay all positive. So it kind of oscillates. So if it's a negative power, the whole thing's negative. And if it's a positive power, the whole thing's positive. You know, it just depends on the power here, doesn't it? The minus is not really. It's kind of.
So it would stay minus. Hold on. So would that be 1 times x to the power 4 plus 4x to the power 3 plus 6x to the power 2 plus 4x plus 1, right?
Yeah.
Okay.
Times that by 1, it's not going to change it, is it? So basically, the answer is that just goes away, and then the answer is that.
Okay.
Okay, guys, so I'll stop the recording around about there.